So today we're going to pick up pretty much right where we left off. On Tuesday, we're talking about GQ coupled, GPCR, G coupled, G protein coupled receptors, GPCRs. And we'll do some calcium work, and then we'll turn into neurophysiology. And some of this will be reviewed from self-phys, but today we're going to get into new material because we're going to actually talk about some equations that are important for membrane potentials, the Nernst equation and the Goldman-Hodgkin-Katz equation that you're going to be using in your problem set, which is due on Sunday. Remember, your problem set's due on Sunday. You can work with other students on this. I have a couple of hard copies here if you didn't pick it up. You turn it in to an envelope at the CST desk. Joe?
When is the envelope at the desk?
When will the envelope be available? After class today.
Okay.
So that's what we're doing today. So here is an image of the GQ story. Let's walk through it. Okay, and you can annotate your pictures. I gave it to you as a handout. Annotate this one. So what's embedded in this arrow? Anybody? The ligand. That's what they're calling extracellular signal, would be the first messenger or the ligand. What happened? What are verbs that happen here? Action words. Binding, and before that, diffusion. Right, so ligand, diffusion, and binding. What happens then? My two favorite words in biology. Conformational change. What happens then to the G protein? Conformational change. What molecules are not shown here that you could annotate your figure with? What happens after the conformational change of the G protein? This is the receptor, this is the G protein, GQ. What happens next? GTP, well, really, what do we have to do to get, before we can get GTP into the story, what do we have to do first? GDP has to unbind, and then GTP binds, further conformational changes, and the alpha subunit and the beta gamma complex both dissociate from the receptor and from each other. Okay, what's embedded in this arrow? Diffusion of the alpha or the beta gamma subunit in the membrane. Remember, membranes are fluid. There's lots of lateral mobility. Things are moving around. And this is not very far away. It might be part of a complex, actually. But there is some diffusion of, let's say, the activated alpha subunit. What is this protein? What's the full name of it? Let's unpack this jargon here. Joey.
Phospholipase C.
Phospholipase C. There are multiple forms of it, which we don't have to worry about. Alpha, beta, gamma, different forms of phospholipase C. Some of them are activated by the activated alpha, and some of them are activated by the liberated beta gamma. I'm not going to get into the details of which is which. Phospholipase C. What's this? Can you see it? My block. What's PIP2? Nobody? It's the substrate on which phospholipase C acts. It's a lipid. It's a phosphatidyl inositol bisphosphate. Phosphatidyl inositol bisphosphate. PIP. Phospholipase C cuts PIP2 into IP3, which stands for inositol tris phosphate. IP3 is inositol tris phosphate, and diacylglycerol. Those are the products of the cutting of PIP2 by phospholipase. Diacylglycerol, inositol tris phosphate. I won't ask you, well, spelling doesn't matter. Let me just say that. I could write these words on a board, and they might even be in your key concepts list already. Anyway, IP3 is water soluble, and diacylglycerol is lipid soluble. What is going on in this arrow? Diffusion of IP3, diffusion of IP3 from the membrane through cytosol to, what does this stand for? Endoplasmic reticulum. Okay, so endoplasmic reticulum, you learned all about that in cell phys. How do we link this arrow, well, what's this? Calcium ion, give that to you. What is this arrow? Diffusion of calcium ion in cytosol. How do we link this arrow, the diffusion of IP3, to this arrow, the release of calcium and the diffusion of calcium from the ER into the cytosol, or through the cytosol? There's something missing here. What is it? A calcium channel, a IP3 gated calcium channel that is expressed on the ER membrane. There are other calcium release channels on the ER that we'll talk about, but now we're talking about an IP3 gated, activated calcium channel. Calcium is stored in the ER. Remember we talked about circa? Well, circa is here because this is ER. It's not a sarcoplasmic reticulum, but it is an endoplasmic reticulum. So circa is here, pumping calcium into the lumen of the ER. The concentration of calcium in the lumen of the ER is high. So when we open up an IP3 gated calcium channel, calcium is released from the ER and diffuses. Let's unpack this jargon. What does PKC stand for? Anyway. Shout it out. Raise your hand, whatever. Protein kinase C. So protein kinase A is activated by cyclic A. Protein kinase C is activated by calcium. It's also co-activated by diacylglycerol. And so in many cases, protein kinase C acts as an inactive form in the cytosol. And then when bound to calcium, it moves, it mobilizes, it becomes membrane associated because of its interaction with diacylglycerol, and it is now an active kinase. And it phosphorylates a lot of things and changes the cells. So there's the signaling pathway for the turning on of a protein kinase, of a GQ pathway. Let's talk about what could turn this pathway off. We talked a little bit about what turned off a pathway in the cyclic A story. Phosphodiesterase is one of the ways that the cyclic A pathway can be turned off because it cuts cyclic A. Phosphodiesterase cuts cyclic AMP into AMP, which is not active. It's not the same as AMP, as cyclic AMP. Let's think about the ways that this could be turned off. What could happen here? The ligand could dissociate from the receptor and undo the conformational change. What could happen here? I'm going to wait for you on this one. What could happen here? So that's true in the cyclic A story, the dissociation of the ligand. Here's another thing that can happen in the cyclic A story. Sophie?
The GTP is hydrolyzed?
The G protein hydrolyzes the GTP and turns itself off, because the hydrolysis of GTP makes GDP, which is the off form. So the G proteins have intrinsic GTP ACE activity. They cut GTP into GDP, turning themselves off, and that is accelerated by other proteins called RGS proteins. I think we introduced that in self-this. Same thing can happen here. RGS, regulators of G protein signaling, assist G proteins in their turning off. Auto turning off. And then it can get tricky. IP3 can get turned off by being recombined with diacylglycerol to make PIP2. There's enzymes that remake PIP2, so that uses IP3. And then there are enzymes that phosphorylate it, that turn it into IP4, which is not the same as IP3, which is also an offish state. Calcium is so calcium can get pumped back into the ER. That's another off pathway. Protein kinase C has some intrinsic control mechanisms. So I guess what takeaway message is here, I have focused on the turning on story, but there are turning off stories that I could ask you to think about, knowing these bits and pieces and the concepts of what it takes to turn a pathway off. Remembering that if we turn a pathway on and we don't turn it off, we typically have a problem, like cancer or some other problem. As always, the blobograms have real structures behind them. Here's the G protein, the GPCR, there's the ligand bound, here's the alpha subunit, the beta gamma complex, in the way it really looks. Three-dimensional bundles of alpha and beta structure. Here is the structure of phospholipase C. As you are standing in the membrane, so you're looking, let's get reoriented. You're in the membrane looking at phospholipase C. So this is where phospholipase C looks to you. Here is an active site. This calcium is not the same calcium that activates PKC, because this is phospholipase C, but it's got a calcium at the active site. So there's the site that cleaves PIP2, and here's the surface to which the G protein binds to turn it on. I won't ask you to know this, but just so you know, active site, this is the surface that where GQ binds. So let's do some problems. So we'll do this as a series of clickers. Three-way clicker. A is yes, B is no, C is maybe. Which of the following would cause an increase in the cytoplasmic, the cytosolic concentration of calcium? Let me be clear, activation of voltage-gain calcium channels is on the surface membrane. Okay, mostly correct answers. The correct answer is A, because the cytoplasmic concentration of calcium is low, normally, the extracellular concentration of calcium is high, here, higher. And so if we open calcium channels, calcium's gonna flow in, and that's gonna increase the cytoplasmic calcium concentration. Questions about, now if you go downstream, if you say, okay, well that'll happen momentarily, but then the ATPase is gonna pump it back up, you're taking it a little bit too far. That's not what I meant. I meant, let's just talk about what's happening right now. Okay, let's talk about activation of calcium release channels, IP3 gated calcium release channels on the ER. You're all getting this very quickly, same concept. Activation of the GS couple receptor. I will accept B, I put in C because it depends on what the GS is coupled to. B, based on what I've told you, B could be a correct answer. Activation of a GQ coupled receptor. Okay, that's another A, right? We activate the receptor, we do the yada yada that I just told you about, we're going to increase cytosolic calcium. Activation of pumps of the calcium ATPases. If we turn them on, is that going to increase cytosolic calcium? No, because if we turn on the pumps, we're pumping calcium from the cytoplasm into the ER, and that's going to decrease cytosolic calcium. Is that clear? Because I saw some wrong answers. You know, again, this is not testing. This is getting the conversation started, but it's not getting a lot of questions. Maybe it's just obvious after I show you the answer. That's fine. Are there questions about any of these? I went through them pretty quick. Oh, we got one more. Activation of a non-specific cation channel in the plasma membrane. So remember, calcium is a cation. Non-specific means any cation. All kinds of colors on this one. A rainbow. Yeah, same as voltage-gated calcium channels. If it's non-specific, means calcium can flow, because calcium is a cation. So even though it allows sodium and potassium also to flow, it allows calcium to flow. Calcium will flow from the extracellular fluid into the cytosol and will activate it, and will increase cytosolic calcium. So those questions, there was a lot of color here. So what was confused? Somebody want to ask a question? Or did I already explain it? I know it's early in the morning and questions are hard early in the morning, but we can come back to this if you like. Okay, so now we're going to turn our attention away from generalities and go into neuroscience. We're going to focus on neurons, nerve cells, and get into some neuroscience. In the past, I have put up this video. It's supposed to be inspirational. We're going to skip it today. I showed it to my wife. She found it super annoying. So we're not going to do it. I find it inspirational. She finds it just get me out of here. So if you're thinking about being inspired, cut and paste this URL into your browser and watch this video. It goes too fast. I'll admit it goes too fast, but I find it inspirational. My wife finds it annoying. We can take a poll and see what you all think. She's not a neuroscientist, so maybe there's the difference. Okay, so here's some review of neuron cellular anatomy, right? This is cellular neuroanatomy. Cartoon version from your textbook. Like all cells, it has a cell body. Like all cells, the cell body has a nucleus. Not all cells, there are some cells that don't have a nucleus, like red blood cells, but whatever. nucleus. Specializations. Dendrites, that's where the receptors are. Typically, that's the input end of the neuron. An axon, that's where the action potentials are. I'm oversimplifying because there can be dendritic action potentials. This is a new field. And information can flow in the backwards, in the retrograde of the classic, but we're going to talk classics. This is where the receptors are, information flows this way, outputs are through the action potentials in the axon, and then we're going to talk about neurotransmitter release here next week. Axon collateral is just a branch from the axon. Just collateral is a fancy name for branch. Here are some actual, what's called camera lucida drawings of actual neurons. So there's the soma, or the cell body of the, this is a cortex, so this is a cell from the cortex of an animal, showing the cell, the cortex being the gray matter of the brain, really. Cell body, multiple dendrites, an axon, axon collaterals. So there's the axon, and some of these are axon collaterals. Here, this has got to be one of the most beautiful sets of cells on the planet. This is a Purkinje cell from the cerebellum, and you've got millions of these, and each of them has this incredible dendritic arborization. Arbor means tree, you can see why. This arborization of dendrites. Cell body, axon, axon collateral. So the cartoons don't do neurons real justice in their complexity. But we have to, so that's something to remember, but we continue to talk about cartoons because it's just easier. So here's a cartoon of a neuron with some labels. We're going to take you're going to take 5 minutes and label. Do the labels of the names that you know. You know what dendrites are. You know what the soma is. You might remember what a node of Ranvier is, or maybe not. You might remember what myelin is and what a Schwann cell is. Do the best you can, labeling the dots. Let's take 5 minutes, and then we'll go over it. I'm going to ask for volunteers, but if there's too much silence and unvolunteering, I'll start phone calling on people, so there's that. Let's do some easy ones first. Somebody tell me what button to press for a nucleus. Oh, maybe what I should do is give you the laser so you can actually point to a button. Who wants the laser? Okay, Matt's going to get us started. There's the gray button. It's the same old one.
Alright, that would be the nucleus.
That would be the nucleus. So I'm just going to do it this way. Here we go. Nucleus. Okay. Sure. Somebody take the nucleolus as the next easiest one. That would be the nucleolus. That's not a name that we teach very much in this curriculum, but that's the nucleolus. Okay, somebody pick a button for axon. Raise your hand, we'll get you the laser. Chelsea.
I think that one?
That's a good one for axon. I mean, there's a couple of them. This could be the axon. I don't remember which is the right one, but this could be pointing to the axon, but that could be pointing to the axon too. So let's just take that one. Okay. Soma.
Okay.
Pretty easy.
Soma?
Cell body, soma.
Oh.
Yeah, right. Here's the cell body. Okay. Node of Ranvier. What brave soul wants to point to the node of Ranvier? Oh, let's have the laser over here. We'll start using this quadrant of the room for a little while. Node of Ron VA.
Like
That's a good
that
one.
one or that one or that one.
This is probably the best. The node of Ron VA is the gap between these cells, the space. So that's not really pointing to the gap, and neither is that. So it's hard to see. But
Yeah.
so that's probably the best indicator of if it's not pointing to the axon, it's a good indicator for the node of Ron VA. Okay. Synaptic knobs, synaptic boutons, synaptic terminals. Charlie.
I just have a clarifying
Okay.
question from the node of VA. It's any unmyelinated gap in between two nodes.
Right. So there's a node of Ron VA, there's a node of Ron VA, there's a node of Ron VA, there's another one, there's another one, there's another one, there's another one. There's probably 100,000 on a given
Okay.
long axon.
Okay.
100,000 might be an exaggeration, several thousand. Okay, where were we? Synaptic bouton, synaptic terminal, synaptic buttons, synaptic term endings, so forth. Okay, I mean, these things here, so this is probably the best label. I mean, it's almost invisible, I get it, but that's probably the best label for synaptic knobs, right? The terminals, the things at the end of the axon. So then what is this label? What is this labeling here? It's labeling all of them. I'm going to give you this one. That's the terminal arborization, the branching, the tree-like structure at the terminal. So this is the terminal arborization, and this is pointing to specific terminals. Okay, let's do dendrites. Who wants to point to some dendrites? JP. Yeah, it's got to be right. Dendrites. Okay. Who wants to do axon collateral? Alexander. Sure. A branch from the axon. Okay. I skipped one. Initial segment. This should really be initial segment or trigger zone. Okay. Yes. This initial segment of the axon is where action potentials are triggered. And it's also called the axon hillock. So, that's why there's two labels here. The axon hillock and the initial segment are both these things. Yes?
Do we need to know the difference between the axon hillock and the initial segment?
No. As far as I'm concerned, they are synonyms. Axon hillock is describing the shape of it, a bump, little hill. The initial segment is describing the fact that it's the beginning of the axon. The spike initiation zone is describing its physiology, where action potentials are triggered. They're all at the junction between the soma and the axon proper. It's a special part of the axon. Okay. Myelin. Who wants to do myelin? Okay. Who's got the lid? I'm tempted to throw it to you, but somebody. Well, it gets pretty easy, right? Because we've labeled just about everything else. Right, so So these cells in the periphery are called Schwann cells. These are the cells that make myelin and wrap the axon with its insulating layers of myelin. So this, and this, how do we differentiate? Okay. The myelin sheath is made by the Schwann cell, and the myelin wraps, and that's what are called internodes, but that's language that I won't use. An internode, so if this is a node, these cells make the internode. These cells are Schwann cells, and they make the myelin sheath. Question, Charlie?
Yeah. So it's true that the composition of myelin is different depending on which subsystem of the general nervous system, right?
In a minor way, myelin is myelin. The composition of myelin is mostly fat and lipid and lipoprotein.
Or is it the
cells are different.
This-
In the,
yeah.
in the peripheral nervous system, which is what is illustrated here, we have Schwann cells. In the central nervous system, we have astrocytes. No, oligodendrocytes.
Why is that?
Why is that? I don't know. Oligodendrocytes are the cells of the central nervous system that make myelin, and Schwann cells are the cells of the peripheral nervous system that make myelin. The function is similar, very much the same. Yeah.
How would you be able to differentiate where the Schwann cell is on this diagram compared to the myelin?
Oh, you couldn't.
Okay.
You couldn't. This is the Schwann cell, and it's just a bunch of myelin.
Okay.
Other questions? These are good questions. Okay, so you can play this game at home. You can print out another copy of this from Moodle and reinforce your memory. Here is an image. Let's see, it's hard to see. Let's see if I dim the lights whether we can see it without you falling asleep. That's not right. So here is a micrograph, a light micrograph of an axon. So the axon, this is the node. Schwann cells or oligodendrocytes, I can't tell which. Voltage-gated sodium channels are highly localized at the node of Ranvier. We're going to talk about action potentials. That's where the voltage-gated sodium channels are. The potassium channels that we're going to be talking about more soon are localized near, but not in, the node of Ranvier. This gray cloud is myelin. So here's the axon. At the node of Ranvier, it's actually quite compressed, and then it sort of spreads out in the internode region. Here is an electron micrograph showing the wrapping of myelin around an axon. So this is taking this part of this nerve, cutting it this way, and looking at it in cross-section. And here's a cartoon of an oligodendrocyte wrapping axons with myelin. And up there is a cartoon of a Schwann cell wrapping axon with myelin. Central nervous system, peripheral nervous system. Not all neurons are myelinated. Some of them are bare. The axon is not myelinated, but many of them, most of them in our nervous system are. Okay, so let's transition to away from cellular neuroanatomy to something that is kind of difficult. Membrane potentials. It's difficult conceptually, and I'm going to ask you to build, this is going to be new material, maybe for the first time in the semester for this class. We're going to build on what you know from self-is and add to it. So let's walk through this. Let's start with a really simple system. We've got a solution of some solvent on both sides of a membrane that is permeable to that solute. That solute can go through it. That's what permeable means. The solute is permeant. The membrane is permeable. That means the solute can go through the membrane. Biophysicists have described, so we've set this up with a concentration gradient. So high concentration of the solute on one side, low concentration of solute on the other side of the membrane that is permeable to the solute. Well, you know what happens. Diffusion happens. And biophysicists have described the flow of solute due to diffusion. The rate of, so this is flux, is flow rate, movement in millimoles per minute or something. It's a rate. It's a constant. We're not going to get into the biophysics of the constant, times the gradient of concentration. X being, so this is the x coordinate. The distance from here to here is a x, a distance. dc dx, or delta c delta x, we don't need to do this in calculus. This is the gradient. The steeper, so let's just unpack this simple biophysical equation. The steeper the gradient, that is to say, the higher the concentration differential in space, the faster the diffusion rate is. That kind of makes sense. And the higher the diffusion constant, the faster the diffusion rate is. It's just a constant. Well, it's not just a constant, because it's got all kinds of biophysics embedded in it. Stokes you've never heard of. Einstein you've heard of. Albert Einstein started his career trying to understand diffusion. Who'd have thought that we'd get Albert Einstein into an anatomy and physiology class? And there it is. Okay, so there's an equation, the Stokes-Einstein equation, defines the diffusion constant. Let me just unpack this. You will not need to know this. The gas constant, the absolute temperature, 6 is the number 6, pi is pi, you know those numbers. Eta is the viscosity. The higher the viscosity of the fluid, the slower things move through it. That makes sense? It's in the denominator. So high viscosity, lower diffusion constant, lower rate. Okay, viscosity, and this RS is the Stokes radius. Stokes gets more of the credit of this than Albert Einstein does. It's probably legitimate. The bigger Stokes radius is the size of the substrate, of the solute. The bigger the thing is, the slower it diffuses. That makes sense too. So you might have said, well, I could come up with that equation. But you didn't. Stokes and Einstein did. Okay, so there's diffusion. Now, let's do now is change only one thing for now, and that is give the solute that we're talking about charge. So we're going to talk about a membrane that is permeable to potassium, which has a charge, and not permeable to anything else. So just like in the previous cartoon, we've got something really simple, a semi-permeable membrane, like a cell membrane, with a high concentration of potassium on one side. Rather than using dots, I'm just going to use the size of the symbol, and a low concentration of potassium on the other side. Let's see, did I do this right? Yeah. So, thinking cellularly, this is dumb and stupid, but thinking cellularly, this would be inside the cell and this would be outside of the cell because of the sodium-potassium ATPs. Okay, diffusion happens because the membrane is permeable to potassium. That's what we did. We set this up as a membrane that was permeable to potassium. Cellularly, this is a membrane that has potassium channels in it. Channels give the membrane permeability, and they're selective. So you could imagine a cell membrane that has potassium selective channels that confer a potassium selective membrane property on the membrane. So I'm not making this stuff up, I mean, this is real. So what happens? Potassium diffuses down its concentration gradient. By the Stokes-Einstein equation. But it's selectively permeable to potassium. There are counterions, of course. There's chloride in here. You can't make a solution of just potassium. If you throw potassium metal into water, what happens? It explodes. It turns into fire. It blows up. We don't do that because we have chloride. We throw potassium chloride into solution, and it just dissolves. So there's chloride here. You can use green for chloride. And it doesn't matter that it's so pale because we're not going to pay attention to it. But it's there. So every time a potassium ion moves, it brings a positive charge to the other side of the membrane and leaves behind a negative charge. The negative charge being the slight excess of chloride on this side relative to this side. That, now we get into the concept of voltage. That separation of charge across a space, the membrane has some dimension, is voltage. That is what gives, that is what a voltage is. Separation in charge in space. So now we've just made a very small voltage across this membrane, slightly negative on the inside relative to the outside. Okay? Now, I'm just going to go to the next slide, but it's the same thing. Let's continue this. So another potassium ion flows down its concentration gradient and leaves behind a negative charge and deposits a positive charge. And another one goes, leaves behind a negative charge and deposits a positive charge. The flow of this gradient, the flow due to charge, no, the flow due to the gradient, the chemical gradient, is the Stokes-Einstein equation. But now we're setting up an electric field, a voltage, that's going to affect the movement of ions. That's what voltages do. This side is negative with respect to this side. So if eventually there's going to be enough flow that we're going to establish a large electrical gradient. What direction do the ions want to move in response to the electrical gradient? Not the chemical gradient, but the electrical gradient. Which direction is the flow due to the electrical gradient? The other way. Potassium wants to flow from positive to negative. So as more and more potassium flows and creates more and more of the electrical gradient, the gradient opposes that flow. And eventually, the two forces, the force for flow due to the concentration gradient, and the force for flow due to the electrical gradient, which also has an equation, I'm not going to get into it, are equal and opposite. Eventually, we reach an equal and opposite condition, and that is equilibrium. Before I go to this, everybody clear why we get to an equal and opposite condition under these settings? In this setting, remember we've got a membrane that is permeable to potassium and only to potassium, and we have set up, using the pump, a gradient. And now we have established electrochemical equilibrium. Valeria.
Can you just clarify the equation that's on this slide?
Okay, sure. So the flow is due to the mobility of the ion times the charge of the ion times the concentration of the ion, even though it's not, you would have to, the concentration of the side from which it's flowing due to the electrical gradient, times the voltage gradient. Okay? So this is a constant, mobility of the ion in solution. This is a constant, charge of the ion in solution. That's a constant. Concentration, we're going to treat as if it's a constant, because the concentration gradients, I mean, the changes in concentration that happen here are infinitesimally small. So we're going to treat this as a constant, whatever concentration happens to be present over here. And then the voltage gradient is what is established by that concentration gradient. And so when we get to equilibrium, let's just be clear, when we get to equilibrium, we have the Stokes-Einstein equation on one side, diffusion times, I'm going to use, how many of you have had differential calculus? You know what dc dx is? Okay, I'm not going to use that. Delta c over delta x. So that was the flow due to the concentration gradient. And now it's equal and opposite. We're not going to get into the charges that define whether it's equal and opposite. But now we have, let's just turn this into another constant times the charge of the ion, because we could talk about chloride, which is a negative charge, or calcium, which has two charges. So, no, we'll just leave it the way it is. So, we don't need to change things. Mobility times Z times concentration times the voltage gradient. At equilibrium, if you solve this as a differential equation, you get what's coming up on the next slide, the Nernst equation. Let me just show you a little bit how that would come. Those of you who like math, so we're going to have delta C over C is equal to mu times Z divided by D times delta V. We're going to turn these deltas into D's. We're going to integrate it. Calculus. and we're gonna get the Nernst equation. So that's what Nernst is he solved this problem. Obviously, I'm not gonna ask you to do this. This was for your, this is so you know where this came from. Solving this differential equation produces the Nernst equation. The Nernst equation, so here it is. Some constants, there's our friend Z, the charge of the ion. So RT over F, those of you who've taken econal might know that RT over F is a constant. Gas constant, absolute temperature, the Faraday has to do with charge. Let's not worry about that. RT over F is a constant at a given temperature. Z is the charge of the ion. Those of you who've done calculus know that if you solve a dC over C equation, you usually end up with a logarithm. That's where the logarithm came from. Integrating delta C over C. And this is the concentration of the ion. And now we're going to try to use cellular jargon. The ion on the outside, concentration, divided by the ion concentration on the inside of the cell. This is delta C. That's what that came from. That's the concentration gradient. On the outside, on the inside. So, every ion has its own equilibrium potential. The cartoon that I showed was setting it up for potassium. But I could have just as easily set it up for sodium or chloride, and with a little bit of a twist for calcium. So that's why we're talking about the equilibrium potential for potassium is RT over F, because Z is 1, times the natural logarithm of the concentration of potassium on the outside divided by the concentration of potassium on the inside. That defines the equilibrium condition for potassium. If the membrane is permeable to potassium and only to potassium. If the membrane is permeable to sodium and only to sodium, the equilibrium potential for sodium, RT over F, Z is still 1, natural logarithm of the concentration of sodium on the outside divided by the concentration of sodium on the inside.
So it's always the extracellular concentration over the intracellular
Yes,
concentration?
it is. For now. So some of you don't like natural logarithms and are happier with the logarithm base 10. But we can convert from natural logarithm to log base 10 just by changing things in the constant out front. Here's another equation. To be clear, I'm not going to ask you to memorize this equation. The thing you're going to be using for the problem set is a simulator, a calculator that uses it for you. I am going to ask you to know the equation, how it works, but not to actually solve a problem with it in an exam setting or quiz setting. Okay, so E is the voltage. So what we solve for is the voltage at which the flows are equal and opposite. RT over F has a constant. Z is the valence, the charge of the ion. Sophie.
To go back to the two equations that you showed that were equal to,
Okay.
which one is chemical and which one is the...
This is the chemical,
Okay,
and this is the electrical.
okay.
Other questions?
Can you go back to the slide? Yeah, so, where did you get the 61 value in this simplified version? Is that because it's not at room temperature?
Nope. This is log base 10. So RT over F is 25. When we convert natural logarithm to log base 10, we multiply by 2.3 or something. But it isn't something like that. And so the 25.5 becomes 61. let me put up the next slide. We'll take a break here. So this is the translation of the Nernst equation into English. Read it as we're taking a break. This is what you need to know about the Nernst equation. Okay, let's take a 4-minute break. The Nernst potential, which is the equilibrium potential for a specific ion, is the voltage that a membrane would have if it were permeable to that ion and only to that ion. This doesn't happen very much in biology, but that's the theoretical basis for the Nernst potential. Corollary to that is at the equilibrium potential, the Nernst potential, for an ion, for a specific ion. That ion is at equilibrium. No, I'm not reading. At the equilibrium potential for a specific ion, that ion is at electrochemical equilibrium. So, the net flow of that ion is 0. For every ion that flows down its concentration gradient, there's another ion that flows down its electrical gradient, which is an equal and opposite. And so the net flow, I'm not saying there's no flow, I'm saying the net flow is 0. Every time an ion moves in one direction, an ion moves in the other direction. There's permeability, so there's flow, but there's no net flow if the membrane is at equilibrium for that ion. No net flow of that ion, to be clear. If the membrane potential is above, more positive, than the Nernst potential for an ion, the flow of that ion, assuming the membrane is permeable, is going to be outward. We're going to use this in a few minutes. If the membrane potential is below the Nernst potential for that ion, that is to say, not as positive or negative below it, the flow of that ion is going to be inward. Remembering that the voltage, the membrane potential, we always define the membrane potential as the inside. That's the key. The membrane potential is always defined inside with respect to the outside. So if the inside is positive above the Nernst potential for that ion, the flow of that ion is going to be outward. If the membrane potential is below the Nernst potential for that ion, the flow of that ion is going to be inward. We're going to use this. I can see some confused faces. You're going to work with this and understand it better when you work with the problem set. So here are some typical values. I think I printed this out for you. Let's not get, so the equilibrium potential for potassium is a large negative number. Let's make sense of that. Remember, the concentration of potassium on the inside is high. The concentration of potassium on the outside is low. Potassium tends to flow from inside to outside, making the inside negative. The concentration of sodium on the outside is higher than the inside because of the sodium pump. So when sodium flows down its chemical gradient, it makes the inside positive. And if the membrane potential gets this high, sodium would be at electrochemical equilibrium. But we hardly ever get there. Same stories for calcium and for sodium. Calcium and chloride. Do not memorize these numbers. So now we're going to get away from pure theory, away from the Nernst potential, to another equation called the Goldman-Hodgkin-Katz equation. So these are three giants of electrophysiology who work together to understand what the membrane, how to define the membrane potential as a function of gradients of ion. Gradients, so here's the potassium gradient, here's the sodium gradient, here's the chloride gradient. This is not a typo that outside is here and outside is here. Why is that? This is getting to Evan's question. The Z of chloride is -1. And so in order to keep it right out here, chloride flips in here. The reason why calcium is not in here is that the Z of calcium isn't 1, plus or minus 1. It's 2, and that screws things up big time. If I were to put this equation up on the board for calcium, for sodium, potassium, and calcium, the equation would go down the hall. It's unbelievable what that 2 does to this equation. It's unbelievable. So we don't do it. So what is this? This is the equation that defines the membrane potential of a real cell in terms of the constants, the permeabilities of that membrane to the various ions, and the concentration gradients of the ions, ignoring calcium. In English, this equation defines the voltage a membrane would have given the concentration gradients and the permeabilities. So this is real, right? Because a membrane is permeable to not just to sodium or not just to potassium. That's what defines Nernst. But now we're getting into a real situation where we have multiple permeabilities. Let's just ignore this. We don't need to know this. This is getting into the biophys system. You're going to use the Nernst-Goldman, so Goldman is shorthand for Goldman-Hodgkin-Katz, and Nernst is Nernst. There is this simulator online. This is the URL for it. So here's how you're going to do this. You're going to cut and paste that URL into your browser, and it's going to pull up a page like this. The Nernst-Goldman simulator. Now things are gotten tricky. So if you launch it, you might get this, which is unpleasant. And this is because my computer requires me to allow this program to run because it runs Flash. You have to enable your computer to run Flash, and then you have to allow the program, the browser, to run Flash. Okay? Whatever it takes. So let's go back. If for some reason that doesn't run, if for some reason you can't figure out how to get your browser to run Flash, if you scroll down, scroll all the way down, you can download it for your Mac or you can download it for your PC, and you can run it from your computer without having to use the internet at all. In both cases, you have to be able to run Flash. And Flash is losing its support. But so before the end of the week, my recommendation is make sure that your computer can run this program. Use IT to get you can do it. But it used to be that this just ran. But now because Flash is losing support, things are getting more complicated. You have to run this program to do the problem set, to do problem 2. So I'm going to launch it. I guess I'd already told it to allow me. So now you just click on it, and here is the simulator running. Can you all see it running here? This is the way it comes up. I'm going to shut this thing up because this is just noisy. This little thing buzzing around in my peripheral vision makes me crazy, so I can just shut it down. And you're going to use the so by clicking on this tab, the Goldman tab, that's running the Goldman-Hodgkin-Katz equation. There it is, at 37 degrees, because that's human body temperature. You're going to have to, the problem is going to ask you, so this is the default settings, which you don't want to use. You're going to change the default settings based on the problem. If you use the default settings, you're going to come up with the wrong answers. So don't use any of the default settings. It's going to ask you to change the extracellular sodium concentration. Okay, well there's the extracellular sodium concentration. If you double click on it, you can just enter what the problem set's asking for. It's going to ask you the extracellular potassium concentration. It's not 10, it's 4.3. Okay? It's going to tell you the extracellular chloride concentration. Okay? So you can change it. Yes?
All these numbers you're typing in right now, those will be in the problem, right?
Those are in the problem set. I'm looking at the problem set. Now, and I didn't change the intracellular ones because I don't want to do the problem for you, but I've shown you how you can enter the data. You have to change the permeabilities. So now, here's my recommendation. Leave the potassium permeability of 100 and change the other ones relative to it. So the problem set asks you, well, the problem set is going to ask you to change the sodium permeability. If it's going to make it 4%. So I'm just going to show you, input, instead of this being 1%, 1 over 100 is 1%, we're going to make this 4%. Okay? So this is now changing the default permeability ratios. There's the equation. Here are the inputs that you're going to make. Here are the Nernst potentials for each of the ions, given what you've inputted here. So this provides you answers. And then the problem is going to ask you to change things and to come up with answers and then to understand them. I will grade both the answer and your short explanation. Questions about the problem set? I do want to introduce the jargon, the terminology. It's not jargon, it's terminology that I want you to become fluent in. So this is membrane potential as membrane potential. If the membrane potential goes positive or less negative, we call that a depolarization, or it's a depolarizing change of the membrane potential. Depolarization. If the membrane potential goes negative or less positive, we call that a polarization or repolarization. If the membrane potential goes more negative than the resting potential, we call that a hyperpolarization. Those are the words that I want you to use in the problem set. We're not going to worry about overshoot. So I want you to understand this terminology. The resting membrane potential, which you are going to understand from the problem set, given the permeabilities and the concentration gradients. And then if something changes it, if it changes it in the positive direction, it's called a depolarization. If it changes it in the negative direction, it's a hyperpolarization. And if we go depolarized and then we go back, it's repolarization. Let's end with some clickers, just on this jargon, and then we'll, I think you have what you need to know to do the problem set. I'm happy to answer questions, but don't wait till Sunday night to send me a question, because I might not be reading my email on Sunday night. Don't wait till last minute. Okay, a specific neuron. Who got my laser? Is the laser still out there? Oh, you do have it.
I stole it.
Thank you. A neuron's resting membrane potential is minus 50 moles. That's just what it happens to be. Relative to a normal neuron, so I'll just show you, a normal neuron's resting membrane potential is more like minus 70. Relative to normal, this neuron's membrane potential is if more potassium channels on this neuron are activated, the cell will depolarize or hyperpolarize. So we are at the resting membrane potential, and now we are going to activate more potassium channels. We're at rest with some number of resting potassium channels, and we're going to activate more potassium channels. The membrane will hyperpolarize. It will become more negative. This is a key thing. In the problem set, when I say add channels, what parameter are you going to change? Are you going to change the concentrations of any ion? No. You're going to change the permeability. You're going to change the relative permeability to, so if you'll see, if your resting membrane permeability was 4% potassium, so we had 4 over 100. No. The resting membrane permeability was 4%, the sodium permeability was 4% of the potassium permeability. But we add sodium channels, we open sodium channels, which permeability do we change? The sodium permeability. We add permeability to sodium. So we would change the sodium permeability. So that's key for doing the problem set. Okay, and we'll do this last one. What direction is potassium flowing through these channels? It's making the membrane potential more negative, but we are not yet we haven't gotten to equilibrium. Potassium is flowing outward because the membrane potential is still above the equilibrium potential for potassium. So there's some more clickers, which I think I'll just put on Moodle. You can do at your own, you can do these as homework. And we will pick up where we left off. If you have what you need for the problem.